This episode examines how engineering evidence for hydrologic and water quality projects is developed, tested, explained, and presented for peer review and operational use. The narration is built only from items in the episode research log. Each chapter separates observed fact, stated assumption, illustrative example, and recommendation. Where the research log limits scope, that limitation is stated explicitly, and conclusions are not generalized beyond the cited material. Chapter 1. The question before the method. Observed fact. Scholarly publishing guidance defines what counts as original research for a particular journal and lists editorial and ethical requirements. Those definitions apply to submissions to that journal, but are not universal rules for every engineering report or platform. Stated assumption. Clarifying the decision that will use the analysis before selecting methods reduces the risk of a mismatch between analysis and use. This aligns with guidance that ties method selection and reporting to intended use in modeling and investigations. Illustrative example. A team asked to assess whether a land management change will alter downstream nutrient loads must know whether the question is about regulatory compliance, trend detection, or operational control. That phrasing determines required model fidelity, data resolution, and uncertainty characterization. The cited review emphasizes tailoring evaluation to intended use rather than applying one universal performance metric. Recommendation. State the decision context and required confidence level before choosing models, data, and reporting format. When preparing material for a peer-reviewed journal, follow the journal's scope and submission guidance so evidence and presentation match the platform's expectations. Chapter 2. Data, models, and intended use. Observed fact. Best practice reviews recommend evaluating hydrologic and water quality models against intended use, including assessments of bias, outliers, and uncertainty. These are methodological recommendations, not prescriptive laws. Stated assumption. Data quality and metadata completeness directly affect the defensibility of model-based claims. Recommended practice stresses documenting data, tools, and methods to support reproducibility and defensibility. Illustrative example. When high-flow observations are sparse or affected by overflow, the model's suitability for predicting extreme event transport is limited unless those gaps and biases are characterized and addressed. Validation metrics should focus on aspects of performance that matter to the intended decision, such as peak timing versus mean loads. Recommendation. Define data requirements and metadata standards tied to intended use, and document how available data meet or fail those requirements. Record data provenance, processing steps, and limitations so users and reviewers can assess suitability. Chapter 3. Validation, uncertainty, and bias. Observed fact. The literature recommends assessing performance, outliers, bias, and uncertainty as part of an evaluation process tailored to model use. These are interpretation and communication recommendations, not regulatory thresholds. Stated assumption. Explicit reporting of uncertainty and potential biases yields better informed decisions than a single deterministic prediction without context. This approach is consistent with the emphasis on communicating uncertainty relative to intended use. Illustrative example. A water quality model can match average concentrations, yet systematically underpredict high concentration events. Reporting only good agreement would conceal a bias important to decisions about extremes. Evaluation should examine and report such biases with respect to decision needs. Recommendation. For every model-based statement used in a decision, document performance metrics relevant to the decision, the presence and direction of biases, and an uncertainty characterization. Use appropriate uncertainty estimation methods, and describe how uncertainty affects the decision outcome. Chapter 4. Reproducible analysis and metadata.
Observed fact. Recommended practices for hydrologic investigations encourage documenting data, tools, and guidelines to support reproducibility and defensibility. This supports verification and reuse, but does not guarantee quality.
Full reproducibility, public data, open model code, and documented workflows best supports scientific scrutiny and operational transfer. Documentation and openness strengthen investigative value and defensibility. Illustrative example: publishing raw data files, processing scripts, model configuration files, and a clear README allows an independent reviewer to rerun analyses and test alternative assumptions. This level of documentation enhances credibility and usability. Recommendation: archive and publish metadata and processing steps to enable independent reproduction of core results. If full openness is not possible, document what cannot be shared and why, and provide sufficient detail for a reviewer to understand and, if needed, replicate the logical steps and choices. Chapter 5. Peer Review and Evidence Limits. Observed fact. Journal instructions describe editorial scope, review processes, and ethical requirements for submissions to that outlet. These define suitability for the journal, but do not by themselves determine the technical quality of any study. Stated assumption. Peer review can improve clarity and defensibility, but does not replace the need for transparent data, methods, and limitations. Transparent reporting supports defensibility regardless of peer review outcome. Illustrative example. A manuscript may be revised through peer review to improve method descriptions and uncertainty communication. Editor and reviewer requests operationalize the journal's guidance. Recommendation. When preparing evidence for peer review, structure the submission to meet the target journal's requirements and include explicit sections on limitations, uncertainty, and data availability. Use ethical and reporting guidance as a checklist so reviewers can fairly evaluate methods and conclusions. Chapter 6. Communicating results responsibly. Observed fact. Review literature stresses aligning evaluation, interpretation, and communication of model results with intended use. Communication should describe uncertainty and limitations proportionate to decision context. Stated assumption. Decision makers benefit from concise statements that connect model outputs to decision thresholds while providing access to supporting detail. This reflects guidance to tailor communication to intended use and stakeholders. Illustrative example. If a prediction shows a non-zero probability that nutrient concentrations could exceed a management threshold, effective communication includes the probability range, main drivers of uncertainty, and recommended monitoring or adaptive actions. This clarifies what the model can and cannot tell decision makers. Recommendation. Present model results with explicit statements of relevance to the decision, supported by uncertainty bounds, bias assessments, and scenario sensitivities. Pair headline conclusions with appendices or repositories containing detailed metrics and data for technical reviewers. Chapter 7. From Pilot to Operational Decision. Observed fact. Reviewed guidance ties evaluation and reporting practices to intended operational use. Moving from a pilot analysis to operational deployment requires a documented transition path addressing data, validation, and uncertainty relative to operational needs. Stated assumption. An explicit implementation and decision framework reduces the risk of deploying an analysis suitable only for exploratory research. The sources advocate tailoring evaluation methods and reporting to the specific use case. Illustrative example. A pilot model validated for retrospective analysis may not meet real-time forecasting needs without additional observations, recalibration, and latency testing. Models should be evaluated against metrics that reflect operational requirements rather than research-only indicators. Adopt a staged framework when moving from pilot to operations. First, define operational performance requirements tied to decision triggers, including accuracy, timeliness, and reliability. Second, map observed pilot performance to those requirements and identify gaps in data, calibration, or latency. Third, specify additional validation tests and monitoring to close gaps, including uncertainty and bias characterization for operational scenarios. Fourth, Document a transition plan with data pipelines, quality control procedures, and governance for updates and revalidation. Fifth, implement pilot monitoring and scheduled reassessment linked to predefined decision thresholds. Chapter 8. A publishable engineering evidence package. Observed fact. Journal guidance and recommended reporting practices converge on common elements: clear research scope, complete data and method descriptions, explicit uncertainty and limitation statements, and adherence to ethical and editorial requirements for a given outlet. Stated assumption. Assembling these elements into a coherent evidence package increases transparency and helps reviewers and decision-makers assess suitability. This follows the emphasis on documentation to support defensibility. Illustrative example. A manuscript prepared for a hydrology journal includes a precise research question tied to intended use, data provenance and metadata, model description and calibration details, performance metrics tied to intended use, uncertainty analysis and limitations, and a data repository link or statement of access constraints. Journal guidance and recommended practice support this structure. Recommendation. Prepare evidence packages with the target audience in mind. For peer review, follow the journal's submission guidance for scope and ethical disclosures. For operational handover, include metadata, code, and documented decision thresholds required by operators. Record limitations and where further work is needed to move from research to reliable operation. Engineering trade-offs, a concise synthesis. Observed fact. The sources emphasize aligning evaluation and reporting with intended use, rather than with a single universal metric. Model complexity versus transparency. More complex models may capture processes in greater detail, but are harder to reproduce and explain. Detailed configuration and provenance records can mitigate this trade-off. Speed versus validation depth. Operational timeliness can conflict with comprehensive validation and uncertainty analysis. Validation depth should reflect operational risk and intended use. Openness versus confidentiality. Open data and code improve reproducibility, but legal or privacy constraints may restrict sharing. Document what cannot be shared and why, while providing sufficient methodological detail. Implementation Decision Framework Summary. Step 1. Define decision context and performance requirements. Step 2. Assess pilot results against requirements and identify validation, data, and governance gaps. Step 3. Choose model fidelity and documentation level that meet risk tolerances while remaining feasible. Step 4. Document uncertainty, bias, and data provenance and disclose limitations. Step 5. Plan for revalidation, monitoring, and governance after operational deployment. Concluding narration. The path from data and models to defensible engineering evidence is not a single algorithm, but a disciplined practice of aligning methods, validation, and communication to the question at hand. The literature used for this episode converges on a central idea. Evaluation, reporting, and reproducibility must be designed with intended use in mind. That design points to concrete actions: clear scoping, targeted validation, open documentation where possible, and candid communication of uncertainty. These sources make recommendations and set editorial expectations. They do not, by themselves, certify any specific study. For producers and consumers of water engineering evidence, the practical responsibility is to match method to question, document what was done, and communicate what the results do and do not show.
The most useful evidence package is not the one with the most pages. It is the one that makes the decision, the method, the data, and the limitations easy to inspect. Begin with the question that the analysis must answer. Then define the performance requirements that matter for that question. Select methods that can meet them, and record why those methods were chosen. Before a result becomes operational, test the gap between research performance and operational need. Check the data pipeline, the latency, the recalibration process, the uncertainty description, and the conditions under which the model should not be trusted. Treat these as acceptance criteria rather than as notes added after deployment. For peer review, make the scope and ethical disclosures explicit. For operational users, Make thresholds and actions explicit. For both audiences, preserve provenance, document processing steps, and state what remains uncertain. If information cannot be shared, describe the restriction and provide enough methodological detail for a fair assessment. The final question is one of alignment. Does the evidence package help the intended user make the intended decision with an appropriate understanding of uncertainty? If yes, the package is ready for its stated purpose. If not, improve the question, the validation, the documentation, or the communication before increasing confidence. Good engineering evidence is not a claim of certainty. It is a transparent chain from question to method, from method to result, and from result to a decision that remains open to review.